So we start talking about carbohydrates. We'll start with the very simplest. That's usually the way to go when we're dealing with these sort of things. Find out what the simplest molecule is that's considered a carbohydrate or a lipid or whatever, and then start from there and then build out. And so in our case, monosaccharides are the simplest. And we'll find out that there's a wide variety of them and from a wide variety of sources. And how they're put together is really, really interesting, and sort of gives us an idea of how these things get broken down in the body and used as energy. So, not terribly surprising. I mean, we're all sort of kind of familiar with carbohydrates. You're always told you're eating too many of them, or you're not eating the right ones, and you should be eating complex carbohydrates and not sugars and all that kind of stuff. Carbohydrates just mean sugars, and sugars in all sorts of different forms, and they're the simplest provider of energy in the body. Basically, we have carbohydrates, fats, and proteins that give us our nutrients. And these are carbohydrates are the ones that give you the fast energy. The most common carbohydrate is glucose. That's the main nutrient that our body uses. Basically, even complex carbohydrates get broken down, converted into glucose, and then that glucose is then broken down, and the energy is removed by oxidizing the carbons. And I'm going to go through how that works as well. So glucose is super, super important, because basically glucose is the only source of energy for your brain. Your brain can't do anything else except break down glucose. Like complex carbohydrates can't do it. So basically the body provides glucose for your brain and for red blood cells, also the only source of energy for red blood cells. And we know they're kind of important too. So bodies break down glucose and other simple sugars through oxidation. I'm going to go through how that works, not in a huge amount of detail, but just to give you an idea, because it relates to a lot of the chemistry we've been doing already. And the thing that I really like to do is relate the lessons we've already learned to what we're doing now, because hopefully if you can make a link between those two, it makes it easier to remember, and they don't become just another detail to remember, but it's something you can actually understand, and that's always best. Okay, so functional groups, for instance, we know what functional groups are. They're the place where chemistry happens. And on carbohydrates, basically there's three main functional groups that we're going to be dealing with. One is that it's a polyhydroxy compound. What does that mean? It's a polyhydroxy compound. What do you think that would mean?
Does it mean like many hydrogens?
Not hydrogens, polyhydroxy.
It has a lot of hydroxyl groups.
Yes, it has more than one. Poly just means more than one. And so for a molecule to be a carbohydrate, it has to have more than one hydroxyl group. It also has either an aldehyde or a ketone. And we'll see why that is in a little while, because it allows them to do a reaction that turns them into a ring structure. So you need an aldehyde or a ketone. Basically, you need a carbonyl group in order to do that. So it's either a polyhydroxyaldehyde or ketone, or it's something that can be broken down into one of those. So where do carbohydrates come from? Well, the main place we get carbohydrates from are from plants. And it's really important that plants be able to do photosynthesis, because that's what photosynthesis does, is it takes CO2 out of the atmosphere, combines it with water plus energy that it gets from the sun, in terms of UV radiation and converts that into glucose. So basically it takes oxidized carbon, and carbon in its most oxidized form is carbon dioxide. Carbon can't get any more oxidized than that because every one of its bonds is now with oxygen. And so basically poor carbon, all of its electrons are going to this oxygen and going to that oxygen. So we call this oxidized carbon. Then it gets converted into glucose. And now it's singly bonded to oxygen in hydroxyls, or singly bonded to hydrogen. So it gets to keep a lot more of its electrons than it did before. And so it goes from what we call an oxidized form to a reduced form. And it's that reduced form of carbon that we will then use to go backwards and do exactly the opposite and oxidize it in our body, releasing that same amount of energy, because basically this is a reversible reaction. We reverse the reaction, get the energy back out, and then convert it back into oxidized form. So it's a good thing that plants figured out how to do that. So the simplest carbohydrate, as I mentioned, is monosaccharide. And as usual, we have either the Greeks or the Romans to thank for the names. And mono, Greek for one. Saccharis is Greek for sugar, so monosaccharis becomes monosaccharides. They can't be broken down into smaller carbohydrates. They are the simplest, smallest carbohydrate that our body recognizes and then can oxidize and undergo, yes, as Vera says, undergo glycolysis. That's right. So the most common one, glucose, is a monosaccharide, but not all monosaccharides have 6 carbons. A lot of them do, but they have to have carbon, hydrogen, and oxygen with this general formula. For every carbon, there's a water molecule. Now, it's not actually a water molecule, but it's the same number of hydrogens and oxygens as a water molecule. And N has to be 3 or higher. So you have to have at least 3 carbons. And we would call that a triose. So tri for 3, and os is basically the root that we use for carbohydrates, for sugars. That's why they're all called glucose and maltose and so on and so on, because os is the word we use for carbohydrate.
When you say monosaccharides, it means one sugar, right? So like, do they mean like one glucose molecule?
No, it just means glucose by itself.
Oh, okay.
Yeah, it means glucose or any other carbohydrate that basically you can't break it down into another one.
Oh, I see what you mean. Okay.
Like sucrose is not, sucrose you can break down into 2 monosaccharides, and then you can't break those down any further. And starch you can break down into, thousands of monosaccharides, but you can't break down glucose into anything else. You can't make a smaller sugar out of glucose, is basically what they're saying. Yeah.
Yeah, because the carbons and the hydrogen and the oxygen numbers, I was like, well, that's more than one. So I was a little confused.
What do you mean?
Because it's C6H12O6. So, since mono means one, I kind of was like.
Oh, yeah. Mono just means you can't break it down into a smaller sugar. That's all. Yeah. Basically, it's a singular carbohydrate. So disaccharides, di meaning 2, are just 2 monosaccharides joined together. And we're going to learn a lot about those bonds that stick them together. So sucrose, like I just mentioned, can be broken down through hydrolysis. And as we sort of noticed, almost all of these reactions involve either water going in and breaking a bond or forming a bond and water coming out. And you'll notice that this is the same same thing here through hydrolysis, generally by an enzyme. And we'll learn that that enzyme is called invertase. That's actually the old name for it. It's called sucrase now. It used to be called invertase. And that gets so the table sugar that you're sort of used to like putting in your coffee or whatever, when you ingest it, that then gets broken down into glucose and fructose. Fructose is another monosaccharide. And when we start looking at them, you'll see that they all look almost identical to each other. It's really quite striking how similar they all look to each other. So that's a disaccharide. And then oligosaccharides contain 3 to 9 monosaccharide units stuck together. And we'll talk about those at the end of our lesson today, because it's really interesting. All the blood typing groups, known as, type A, type B, type AB, type O, they're all based on oligosaccharides. And so we'll learn what the combinations of monosaccharides are that make blood groups, and why certain blood groups are universal donors and why others are universal acceptors. We'll learn why that is. I find that part really interesting too.
Is oligosaccharides? I've heard of polysaccharides, which means more than one. Is that the same as oligosaccharides?
Oligosaccharides are between 3 and 9, and actually I'm just going to talk about polysaccharides next. Polysaccharides, when you have 10 or more. So basically, there's like 2 different classes of bigger than 2 saccharides. You have singles, you have doubles. Those are the really, really common. Then oligosaccharides, which there aren't too many, but polysaccharides, there's a lot of them. And some of them are huge. So I'm going to go through like the sort of the main types that we come across. The first one is called starch. We're probably all familiar with starch. You get starch in potatoes, have a lot of starch in them. Pasta has a lot of starch in it. What is that? Well, that's just a really long chain of monosaccharide units joined together. So more than 10. And they can either be in one long continuous chain, or you can branch them. Now, starch has branched chains of glucose. Starch is all glucose, and we'll find out cellulose is all glucose too. So it just contains branched chains of glucose, and you can just basically pick them off one at a time, turn them into glucose, and then digest them. So that's why a lot of long distance runners will eat like a lot of pasta the night before a race, because they want to build up their store of carbohydrates, because they're going to need a ton of energy the next day. And so you want something that you can break down relatively quickly and convert into energy. And unfortunately for some of us, fat doesn't do that. Fat takes much, much longer to break down into energy. Starch you can break down very, very quickly.
And I'm curious, is that the reason why they won't? I mean, because usually I would think they'd eat something that's like protein, right? Or is it because protein, it takes too long to break down that?
Way too long.
Okay.
Yeah. So they basically call it carbo loading, because you want a big store of energy, because you're going to be using a ton of it. And so you want something that can be burned fast. So, and starch, you can break down, those enzymes break down basically directly into glucose. And then glucose is the fastest form of energy. You can break that down very, very quickly. Proteins take a lot longer, and they'll provide nearly the energy. Basically glucose, that's the only purpose for it, is to provide energy. That's it. That's all it does. And unfortunately, if we don't use it right away, then it gets converted into fat, gets converted into very long chains of fatty acids. And so that's a whole other thing that I don't think we're going to have a chance to get to the last chapters on metabolism. I know you're all just very disappointed, but we probably won't get a chance to get to that. So let's talk about their functional groups. We mentioned them already. So this is what their structures look like, and you can see how similar they are. So you start with either an aldehyde or a ketone. And so for glucose, it has an aldehyde functional group. And so we refer to it as an aldose, al for aldehyde. So we have the aldehyde functional group, and then we have 1, 2, 3, 4, 5 hydroxyl groups. So that's a lot of hydroxyl groups. And then each one of those can be plucked off and basically oxidized, turned into energy, as well as the aldehyde group on top. Now, fructose doesn't have an aldehyde at the first carbon. We call the carbon that has the aldehyde functional group, we call that becomes carbon 1, because we know that aldehydes are higher up the food chain than hydroxyl groups. So that becomes carbon 1, and then 2, 3, 4, 5, and then 6 down here at the bottom. So fructose is a ketone, and we know the difference between, what's the difference between an aldehyde and a ketone?
Is it one comes at the end of the chain and then one, something like it comes in the middle?
Mm-hmm. Right. So ketone or an aldehyde is always at the end, basically, because what's the difference? They each have a carbonyl group, and they're each have connected to another carbon. But what's the difference on the other side? What's this X with a aldehyde? What is X?
Carbon.
That would be the ketone. A ketone has the carbonyl group, and then it's that carbon that's connected to the oxygen has a carbon on one side and a carbon on the other side. You see? Carbon there, carbon there. But what about the aldehyde?
It has a hydrogen.
That's right. There's a hydrogen on the other side. So this carbon, which is connected to our oxygen, double bonded to make the carbonyl group, is connected to a carbon on one side, but a hydrogen on the other side. That's why it's always at the end. So a ketone group will always be, like we were mentioned, either in the middle or somewhere in the middle, but it won't be at the end. But we still have the carbonyl group. And so we call those ketoses rather than aldoses. And fructose is a ketose. So it has a carbonyl. Now we call that position 2, just because even though it has a higher functionality than the others, but basically we want to keep the same numbering system. So we go 1, 2, 3, 4, 5, 6. So ketose will have a carbonyl at position 2. Aldose will have a carbonyl at position 1. That's basically the only difference between them. You can see that everything else is pretty much the same. Even have the same number of hydroxyl groups, but in slightly different positions, and that'll become really, really important. So I wanted to introduce this part because what we've been learning about the reactions that different functional groups undergo can be related here to understand how carbohydrates are used for energy. So when you have a hydroxyl group, oops, let me go back. When you have a hydroxyl group like that, when we oxidize a hydroxyl group, what's the product? Remember, if we have a carbon attached to a hydroxyl group and we oxidize that, What's the product of that?
CO.
C double bond O, right? Because now this carbon goes from being singly bonded to oxygen to being doubly bonded to oxygen. And if it's at the end of the molecule, it gets turned into an aldehyde. And if it's in the middle of the molecule, it gets turned into a ketone. So what happens when we oxidize an aldehyde? What's the next product?
Carboxylic acid.
Carboxylic acid, that's right. So we go from a hydroxyl group to an aldehyde to a carboxylic acid. But here's something we haven't thought about. What happens when we oxidize a carboxylic acid? We haven't really talked about that. How can this oxygen, how can this carbon, because that's who we're oxidizing, become any more oxidized than this? What's the only way that carbon could be even more oxidized?
You remove the hydrogen?
So if you remove the hydrogen,
Is it possible to do like two double bonds of two oxygens?
yeah, you can. What would that be?
Oh. See, carbon dioxide.
Carbon dioxide. That's right. So what happens in your body is that basically, one at a time, each one of these carbons gets oxidized. First, the top aldehyde gets oxidized into a carboxylic acid. Then that gets oxidized into carbon dioxide. And then where do you think that carbon dioxide goes? You breathe it out. That's where all that carbon dioxide you breathe out comes from. It comes from the oxidation of carbon during metabolism. That's where all your energy is coming from. Because basically you're doing exactly the opposite reaction that plants do when they do photosynthesis. They're taking energy and putting it into the molecule by reducing the carbon and getting rid of the oxygen and replacing it with hydrogens and single hydroxyl groups. And then we do exactly the opposite. So what your body does is it splits off these carbons one at a time. So after it takes off the top one, it then moves to the next one. And it turns that into an aldehyde, which turns into carboxylic acid, which turns into CO2. And at each step, you're removing energy. You're getting energy out of it that you can use for, doing whatever it is you like. So that's how carbohydrates are used for energy. And these are reactions that we've learned already. The only one we really haven't gone into is how do carboxylic acids turn into carbon dioxide. But you can pretty much see how that happens just by removing the hydrogen. These electrons go back to the carbon, and then it splits off. That carbon-carbon bond breaks, and then you're left with CO2.
So I notice a lot of these reactions in biochem and ochem, it's always about some sort of like dehydration or
Mhm.
removing a hydrogen and then, so is that the main basis of biochem and ochem?
That's a lot. I mean, that's not really. I mean, it's the basis of a lot of synthesis reactions and breakdown reactions. Either we remove water to create a new bond, or we add water across a bond. So there's that reaction is done over and over and over again. And that's because that's when you do if I was just to go back for a second, the other product would be water. So when you burn carbohydrates, you would get CO2 and you get water. And in your body, you get exactly the same thing. Only instead of one step, we break it down into like about 40 steps and get energy out of each one. So we much more efficiently retain that energy. But it's basically the same reaction. So this is just another way of looking at the molecule. So again, we're just sort of looking at the functional groups. We've got an aldehyde here. We've got an aldose. So we got the aldehyde head group. And then what's going to become really, really important is the position of these hydroxyl groups. That is going to be crucial. And then the hydroxyl group on the bottom. But these 4 carbons will be super, super important for determining what monosaccharide it is and whether or not we can break down that monosaccharide in our body. And notice that we have these wedge shapes. What do the wedge shapes mean? These wedge shapes here. What do those mean? Remember when we were drawing 3-dimensional representations of different molecules, we use these wedge shapes. What did they refer to? Or what did they tell us?
Their location is in front.
Yeah, their location. So does that mean they're flat, or what do they mean?
Isn't it tetrahedral? I mean, should be in front when they're wedged.
That's right. Excellent. Yeah, it means those carbons are all tetrahedral, meaning they have 4 different bonds. And the wedges mean they're coming out at us, like woo, coming out of the plane toward us. And so this is the way we're going to look at monosaccharides like this, basically flat, lying down, and then we're going to look at the hydroxyl groups, whether they're pointing up or down. And we're going to draw them as if they're all pointing up, because that's basically the way they look like in their structure. All the hydroxyl groups are pointing up in the same direction. And so we're going to use something called a Fisher diagram, and we're not going to bother with the wedges anymore. We're just going to use lines and assume that the lines mean that they're coming up. And that'll be super important when we're talking about what kind of monosaccharide they are. So these are the Fisher projections I was telling you about. So what these are, basically, they look like they're flat, but all of these hydroxyls are coming out towards us, and all these hydrogens on the other side are coming out at us. So we would call this aldo hexose because it has 1, 2, 3, 4, 5, 6 carbons. This molecule we would call keto because it's got a ketone functional group, and it has 1, 2, 3, 4, 5 carbons. So we would call that a ketopentose. Okay, so the difference between them is just where the carbonyl group is. On an aldose, it's on the first carbon, and on a ketose, it's on the second one. That's the only difference. And then basically the rest of the molecule is put together exactly the same way.
What does the end of OSE mean?
That means sugar. Ose means sugar.
Okay.
Glucose, sucrose. galactose. We're going to talk about galactose in a minute. Fructose. It just means sugar. Basically shorthand for sugar, for saccharide. So let's look at these 4 molecules and determine, looking at who the hydroxyl group is attached to. Are they primary, secondary, or tertiary alcohols? Hopefully everyone remembers the difference between them. So what about A? How do we determine whether an alcohol is primary, secondary, or tertiary at the beginning? What would a primary alcohol look like?
Connected to only one carbon. Right.
Nope, close. Because each one of these hydroxyls is attached to only one carbon.
Is it the carbon that's binding to the alcohol?
Right, it's
that's
exactly. It's different from amines. Amines are basically just a nitrogen molecule, and we determine whether it's primary, secondary, tertiary, or quaternary by how many carbons it's attached to. Now, it could be, if it's attached to 1, then it's primary, 2, secondary, and so on. But with hydroxyl groups, they're attached to only one carbon at a time. So we have to look at the carbon that it's attached to. So we have to look at this one. So it'll be that one, that one, that one, and that one. So for A, would that be primary, secondary, or tertiary? Basically, we're asking how many carbons is that carbon attached to, the one that's attached to the hydroxyl group? How many carbons is it then connected to?
Is that a tertiary?
Yes, it is, because it's attached to 3 carbons, one there, one there, and one there. Right, so that's tertiary. What about B?
Secondary?
Secondary, right, because it's attached to one there, one there. So it is secondary. What about C?
Primary?
Primary, right, it's only attached to one other carbon, this one right there. Excellent. And then what about D?
That'd be secondary.
Secondary as well, right. So it's got 1, 2. So secondary. Great job.
So with these, you actually look at, so whatever the carbon is connected to the OH, you look at whatever that carbon is connected to.
Right,
Okay.
right. Because unlike amines, hydroxyl groups only make 1 bond. Amines can make 4. So that nitrogen can make 4 different bonds if necessary, but hydroxyl groups only make 1, because oxygen only makes 2 bonds. So one is with the carbon, the other one's with the hydrogen. It can't make any more. Or actually, it won't make any more. So hopefully you remember the rules about what can be considered a carbohydrate. You think you do? Let's see. So A, is that a carbohydrate? What 2 things do you need to be a carbohydrate? Actually, it's 3 things you need to be a carbohydrate.
Aldehyde, ketone, and it was
Right. You have to have an aldehyde or a ketone. What
And
else?
hydroxy.
How many hydroxy groups?
Is it at least 1?
You need more than 1. Remember, it's a polyhydroxy compound. You need at least 2. and you need at least 3 carbons. So all of these have 3 carbons, so they all could be carbohydrates. But let's look at A first. Could that be a carbohydrate?
How many hydroxyls do you need?
You need at least 2.
Then yes, that would be one.
That's right, it is. Because it has an aldehyde group, it has a hydroxyl there, and it has a hydroxyl there. So it has at least 2 hydroxyl groups. So that is a carbohydrate. That is known as glyceraldehyde. Got an aldehyde, it's got 3 carbons. You remember glycerol had 3 carbons. And so therefore we call it glyceraldehyde. That is a carbohydrate. What about B?
It's missing an aldehyde or a ketone group, so I think
That's-
no.
That's right. So it's got the 3 carbons. That's good. It's got more than 2. It's got 2 or more alcohol groups. That's good. But right, it doesn't have the functional group in order for it to make a ring. It doesn't have an aldehyde or a ketone. This is actually glycerol. 3 carbons, 3 hydroxyl groups. That is not, however, a carbohydrate. It's very important for making triglycerides, which is what you broke down to make your soap, because it was this molecule that was bound to the 3 fatty acids that you then released by your saponification reaction. So this was the thing that kept them together. So it's a very important molecule, just ain't a carbohydrate. What about C?
Yes,
How come?
because it has the aldehyde group. It's got 3 carbons and it has at least 2 of the hydroxyls.
That's right. It checks all the boxes. So it's got more than 1 hydroxyl group and it has a ketone. So we're good to go for that one. Now, what about the last one? What about D?
No,
How
there's
come?
only one OH group.
That's right. It only has 1 hydroxyl. So that would not be considered a carbohydrate. If this was oxidized, and then you put a hydroxyl group there, then it would be a carbohydrate, but it isn't until it gets another hydroxyl group. Great job. So the naturally occurring monosaccharides that we see usually have between 3 to 7 carbon atoms on a molecule. And you asked about ose, that basically is the suffix for sugar. So monosaccharides of specific sizes are indicated with names composed of the number of carbon atoms and the suffix ose. So triose, tetrose, pentose, hexose, heptose. And then we would call them aldose with the aldehyde and ketose because they have a ketone group. So that's where the ose comes from.
I'm curious, can you answer the reason why too much, like the keto diet, why would, to a certain extent, why would that not be good for you? Because I just remember something about having too much ketones in your blood system isn't that good for you or something like that.
Oh, it isn't. Yeah, that's one of the tests. Basically, they test your blood for the presence of ketones to see if you're not digesting things properly. Basically, if you're building up ketones in your blood, is because you're not breaking them all the way down into carbon dioxide and releasing them. So too much ketones, yes, is a bad thing. But I admit I know bupkis about the keto diet. I couldn't tell you a thing about it.
Oh, no, I was just wondering, like, do you know the specific reason why too much ketones is not good for your body?
Well, they're active, they're chemically active molecules. You don't want them floating around free in your bloodstream because we've seen how chemically active they are. aldehydes and ketones, and we'll see, we'll give you examples here in just a minute. They're very active. They basically, what they would do is form chemical bonds with things they're not supposed to, and we would call those adducts. So we would have molecules with these functional groups on them forming complexes on molecules that they ain't supposed to, and causing a lot of problems. So you don't want a lot of really active chemical compounds floating around in your body free, because then they could undergo reactions that they're not supposed to undergo. So that's why you don't want those.
You mean like free radicals?
Exactly. Yeah. I mean, it's your body undergoes reactions with radicals all the time, but they're contained, sort of like a nuclear reactor. You know, you keep those things under wraps, but if it gets loose, then it can cause havoc. So you don't want these things uncomplexed with enzymes just running around your blood, causing all sorts of reactions they're not supposed to. So now we get into the really important part of monosaccharides, and it sort of goes back to three-dimensional shapes and stereoisomers. So I want to spend a good amount of time on this because it's really, really important to understand. So if we remember, a stereoisomer basically has the exact same structural formula as another compound, but the arrangement of atoms in three-dimensional space is different. And remember, we talked about chirality. And chirality is when a carbon, generally a carbon, had 4 different groups attached to it. And those 4 different groups, because it's a tetrahedron, could be in a lot of different orientations, and each orientation was unique. So we're going to learn that there's different forms of stereoisomers. One is called an enantiomer. We didn't really talk about that before, but an enantiomer. Basically, we did mention it. They were stereoisomers that were mirror images of each other. Remember, I sort of gave the example of your hands are enantiomers. They both have 4 fingers. They both have a thumb. Basically, they're the same size, the same shape. Everything about them is the same, but they're mirror images of each other. You can't put one on top of the other. They just don't fit. You can put them back to back, but you can't put them back to front on each other. They're non-superimposable. So we call those have a special name. We call those enantiomers. That's going to become super, super important. And as I mentioned, chiral carbons have 4 different groups attached to them. So if a molecule has more than 1 chiral carbons, it usually will exist as 2 or even more stereoisomers. And we're going to find out that those 4 carbons that I mentioned in glucose, for instance, all 4 of those carbons are chiral. And so glucose can form just a staggering number of different enantiomers. So a compound with a single chiral center can exist as 2 enantiomers, but then it gets really complicated when you have more than 1 chiral carbon. Then you can form a lot more. So let's look at the different examples. So this just goes to exactly what I just said. Here we have glucose, and we're drawing it with the hydroxyl groups coming out at us. And each of these carbons is chiral. That one, that one, that one, and that one. Carbon 1 isn't chiral because it's not tetrahedral. It has a double bond on the carbon. So it is basically locked in place. It doesn't have 3 different things bound to it. It only has 2. So that's not chiral. How come carbon 6 isn't chiral? It's tetrahedral. How come it's not chiral?
Two hydrogens.
Right. It's got two things that are the same. So it can't be chiral. So it's only these four in the middle. So therefore, glucose has 4 chiral centers. So it can form, we're going to find out, 2 to the 4th different stereoisomers. It can form 16 different molecules. And the really mind-blowing thing, it can form 16 different molecules. We only use one of them. Your body only recognizes one. So I've always found that bizarre. So here's just what I mentioned. The general formula for determining the number of stereoisomers is 2 to the n. Let me go back. 2 to the n. N being the number of chiral carbons in the molecule. Glucose has 4, so that makes 16. But we only digest one of them. The other 15 versions, and we don't really actually even see the other 16 versions, plants make one. They make one kind, and we digest that one kind. And the other 15 are not found naturally. I shouldn't say, well, 2 of them are found naturally. The other 14 we don't even see. And I'll show you what the differences are. So here's like the simplest carbohydrate. Remember I mentioned this, we looked at this a little earlier. This is glyceraldehyde. And so that's like one of the simplest and smallest carbohydrates. It has the aldehyde group and it has 2 carboxyl groups. It only has, how many chiral carbons does glyceraldehyde have?
Just one?
Just the one. That's right. Just the one in the middle. Just that one. Everybody else, the other 2 carbons are not chiral. So if we look in the mirror, the only difference between the glyceraldehyde is the position of the hydroxyl group and the hydrogen. On this one, the hydroxyl group is on the left. On the other one, the hydroxyl group is on the right. They're mirror images of each other. And since the other 2 aren't chiral, we don't really even consider them. We just look at the positions of the groups on the chiral carbon. And so the only difference is the hydroxyl group is on one side, hydroxyl group's on the other side. This is what the Fisher projections look like. We don't even include the carbon. We just have wherever we have a cross, that's where the carbon is. But what it helps us do is make a really simple breakdown of, remember, we're considering these to be coming out. So wherever there's a cross, that's a chiral carbon, and the groups connected to the cross are considered coming out of the plane. So the cross is a chiral carbon. That's, since it's the only one, we just are looking at the position of the hydroxyl group. And one we call L, and the other we call D. And if you're wondering why that is, it's because, remember I sort of mentioned that polarizing light. If we shine a polarized light, which is basically light going in just one direction, just vibrating, it's waves going in a single direction. It will bend when we put that polarized light through a solution of L glyceraldehyde. It will rotate that light to the left. And if we have a solution of D-glyceraldehyde, it will rotate it to the right, or dextro. And so we call it D. So, and those have stuck. Those have basically stuck with us. We consider them the L form and the D form. And sometimes they're referred to as the R and the S form, but in biology, That's basically, that's for chemists. For biology, we refer to them as L and D. And we'll get into how we define those in a second. Any questions
because
so far?
I'm curious, is it because the shape of it looks like an L and the shape of it looks like a D?
No, it's because of the rotation of the polarized light when we put them through. One rotates the light in one direction to the left, and the other rotates the polarized light to the right. Basically, you send the polarized light going in like straight up and down, and then when the light that comes through that solution is then vibrating in this direction or vibrating in that direction. And it's the position of the chiral carbon that does that. Don't ask me to explain that to you. That's like physics that are beyond me. But I have done those experiments, and it's really quite weird why the light rotates like that. But that's where we get L and D from. So in the 3D projection, remember, we usually would draw the 3D projection with the wedges, and those represent groups coming out at us. And then the dashes, remember, if we had a dash, the hydrogen that would be behind the plane. So the Fisher projection makes it a little easier for us, because then we just have crosses, and wherever we have a cross, there's a chiral carbon. And we just assume that these are wedges, that they're coming out of the screen for us. So we don't see the chiral carbon, it's just where the lines cross. So that just represents a carbon, and then the two groups attached to the carbon on either side. And then the designation of D or L is based on this Fisher projection. And so I'll show you that when we draw a Fisher projection, we'll be able to tell whether or not the monosaccharide is a D or an L. And that's really important for biology, because we digest the D form and we do not digest the L form, only the D. D for digest. It's not actually what it means. So let's look at these two enantiomers. So I've got D-glucose. So what is a D sugar? How do we tell what a D sugar is? Well, we want to look at the chiral carbon that's farthest from the carbonyl. So the carbonyl group is carbon 1. And what is the chiral carbon that's farthest away from it? 2, 3, 4, 5, right here. So we want to look at carbon 5, and we want to see which side is the hydroxyl group. If it's on the right side, it's D. If it's on the left side, it's L. So that'll be a little easier to remember. If it's on the left side of the Fisher projection, it's L. If it's on the right side, it's D. Okay, most of the carbohydrates found in nature and all the ones that we break down in our body are D sugars. So this, remember, this is only one of the 16 possible enantiomers of glucose, because we're not even considering carbon 2 or carbon 3 or carbon 4. We're just considering the two positions on carbon 5. That makes D glucose. So any questions about L and D? You want to look for the chiral carbon farthest away from the carbonyl group. And the same thing on the ketone. When the carbonyl group is on carbon 2, you're also going to want to look at carbon 5. So we're always looking at carbon 5 to see whether or not it's an L sugar or a D sugar. Because basically the position of all these other groups turn them into different sugars. It will no longer be called glucose. It'll be called galactose or maltose or something else. It'll be called something else. It won't be glucose anymore. It'll be a different sugar.
Does it really matter if it's L or D sugar? I guess it does if you're.
Oh, it certainly does. Your body won't break down in L form. It'll just go right through you. You can't break it down because your enzymes in your body are super, super specific for shapes. And just moving one hydroxyl group means it's the wrong shape and it won't fit in the enzyme. And so it can't be broken down. So basically it gets tossed. So unless it's the D sugar, we can't use it. Luckily, D sugars are the only ones we eat, so don't have to worry about it. So look at the difference between L and D. So here are two Fisher projections. And notice what I want you to really pay attention to is that every single hydroxyl group is on the opposite side, right? If they're mirror images of each other, every single group has to be opposite to each other. So this hydroxyl group is opposite, this one's opposite, but the only one we pay attention to tell us whether it's L or D is the last one, the one furthest away from the carbonyl group. So carbon 5, that's the one that tells us whether it's D or whether it's L. L is on the left, D is on the right. So we call these enantiomers because it's the same molecule, but exact mirror images of each other. Now, if any one of these hydroxyl groups are on the same side, they're not enantiomers anymore. We would call them something different. Anyone know what the other term is? For instance, if I were to change this to hydrogen and hydroxyl, so they're on the same side, they're no longer enantiomers. Do you know what they're called?
Diastereomers.
That's right, man, you're just crushing it. Did you read the next slide or did you know that?
I read the next slide.
Yes, they're called diastereomers. So they are not exact mirror images. And this is the thing that I just find so interesting about these things. Each one of these molecules is identical in terms of their chemistry. They all have the same group, position 1. They all have the same number of hydroxyl groups. They all have a primary alcohol, a carbon 6, but they're 3 different molecules. This one is glucose that we're familiar with. This is galactose. The only difference is the relative positions of the hydroxyl groups. You can see that these are on the same side. These are on the same side, but these are switched. That's it. We've just moved one pair. We just moved one hydroxyl group from one side of the molecule to the other. Now it's a completely different molecule. It's not even glucose anymore. It's galactose. And when your body, galactose fuses with glucose to make sucrose. We'll learn that in the next part. But your body can't digest galactose either. So what does it do? It enzymatically gets changed back to glucose. That hydroxyl group gets moved to the other side of the molecule. Now it's glucose. Now it can be broken down. But galactose by itself can't be broken down until it's been changed back into glucose. And then this other one, talose, has even more changes. And we don't really see talose that much. So yeah, it's really important to understand the difference between enantiomers, which are the same molecule, and diastereomers, which are not. So, because notice both glucose and galactose are both D. Why? Because carbon 5, they each have the hydroxyl group on the right side. So they're each in the D form, but still that's not enough for it to be the same molecule. Everything has to be swapped rather than just that one thing. All right. So let's have a check. Now, here we have we have pentoses actually. We have 5 molecules, 5 carbons, so they're each a pentose. Now, are they D or L? And is it an aldose or a ketose? Let's look at A. First, is it D or L?
D.
Why is that?
What do you call that? Is on the right.
What do you mean, what do you call it is on the right?
The hydroxyls are on the right.
There you go. The hydroxyl, the last hydroxyl, that's the key. The last hydroxyl on a chiral carbon. That's important because there's a hydroxyl here as well, but it's not chiral. So we don't consider it. Right, so that is a D form. Is it an aldose or a ketose?
Ketose.
Ketose, why?
The carbon is double bonded to an oxygen in the middle.
Means there's a carbon on both sides. Yeah, it's not the end carbon. It's not the terminal carbon. So yeah. So because they both have a carbonyl group, the difference is 2 carbons connected versus 1 carbon connected. So let's look at B. First, is it a D or an L isomer?
L.
Why?
The OH the carbon 4 is on the left side.
That's right. That makes it L. Now,
And
was
that's
it
an aldose because
aldose?
there's a H on the terminal.
So what do we call that group?
Aldose.
What do we call this group though?
Oh, aldehyde.
Aldehyde. Excellent. Yeah, why don't we take like a 5-minute break? I've been sort of yelling at you for quite a while. We still got quite a ways to go. So why don't we take, let's take 10 actually. Everyone can like go to the bathroom, get a drink or whatever else. Okay,